fundamental question in mathematics is whether certain formulas or equations have solutions. So consider, for example, this equation here. There exists an x such that ax squared plus bx plus c equals 0. We all know that in R we can express the solvability of this equation as using the condition a not equal to 0 and b squared minus 4ac greater than equal to 0, or a equals 0 and b not equal to 0, or c equals to 0. Over c, the whole thing is even easier. There, we can just express it as follows: a equals not equals 0, or b not equals 0, or c equals 0. Right? So we only need to exclude the case where the constant c is alone and not equal to 0. If you look at these formulas on the right-hand side, you will notice that these are quantifier free. And they give us, quantifier free formulas give us often a nice test for whether a solution exists or not. They are much easier to handle than quantifiers, formulas with quantifiers, because they, for example, don't involve unbounded searches. So we can ask in general, under which circumstances is a formula equivalent to a quantifier-free one. And that takes us to the topic of quantifier elimination, which we will start exploring on the following slides. Here's the definition. A theory T, an L theory, admits or has quantifier elimination if for every L formula phi there exists a quantifier-free formula psi such that over T, phi and psi are provably equivalent. A simple example of a theory that has quantifier elimination is the theory of dense linear order without endpoints. So recall we just denoted that simply by DLO. And if you want to prove this, here's the core idea. So we'll denote a certain kind of quantifier-free formula by sigma x1 up to xn, and we will call that a variable condition or constellation. Those are formulas of the form, let's say x1 greater x3 and x2 equals x4 and x4 less than x3. So any formula that is a conjunction of those basic formulas over the language of orders, right? And these are possibly inconsistent. So there might not be a satisfactory assignment to those over a structure. But let's call this a variable constellation. And now given a formula phi over the language of linear orders, right, we now check, is phi satisfiable in, or phi satisfiable in Q? Let's say via a tuple A, right? Then this tuple satisfies a certain constellation, right? A satisfies some variable constellation sigma sub A. We can now collect all the possible variable constellations that arise from satisfying assignments to phi in a single formula. So let's call this psi sub phi of x is the OR of all the variable constellations that arise this way, rising this way, as some sigma sub A that satisfy phi in Q. Well, there are only finitely many variables, so there can only be finitely many variable constellations. And among those, we pick out those that can be obtained by looking at how satisfying assignments, how the values that we assign to the AIs there relate to each other, right? And those we collect in one big formula, psi sub phi. And then it's actually not hard to see that Q then has the following property: phi sub x implies psi sub phi of x. But on the other hand, with a little bit of work and using the strong automorphism properties of Q that we've seen before when we looked at the Aleph naught categoricity of DLO, right? You can also show that Q satisfies psi sub phi of x implies phi of x. Right. And since this formula here is quantifier free, right, that will be our candidate for a formula, that quantifier free formula that is equivalent to phi. Of course, we're not working directly with T here, but with Q. But since T is complete, the nice property then is that if we can work with show it before a model, we automatically show it for a theory because all models are elementary equivalent. Right. We've only also touched on the case here that phi is satisfiable. If phi is not satisfiable, we have to do a little bit something different, but it's also not hard to figure out. As I mentioned on the previous slide, a main feature of this proof is the completeness, and that we can actually work with Q instead of T and directly use the properties of Q here. Unfortunately, completeness of a theory is not sufficient for quantifier elimination. And an infamous example is the theory of the natural numbers, which we'll later see definitely has not quantifier elimination. Another property of Q, which of course implies the completeness, that we could take a little bit as a guiding principle here, is that Q elementary embeds into all models of DLO. And while we cannot, of course, expect every theory to behave so nicely, to have like one model that's actually called a prime model sitting inside there in all the other models, this idea of comparing substructures with respect to being just a substructure or an elementary substructure actually will give us a nice criterion or test for quantifier eliminations that we can use later on. In order to develop these more usable tests for quantifier elimination, we need to recall a couple of important semantic properties of quantifier-free formulas. One had to do with quantifier formulas and the property of being substructures. So let's assume M is a substructure of N, and A is a tuple from the smaller structure. And let's suppose phi is a quantifier-free formula. So phi quantifier-free. Then these formulas persist with respect to the satisfaction relation between those structures. So the formula, quantifier-free formula phi with assignment A holds in M if and only if it holds in the bigger structure. So that's one important fact that we will need. And related to that is that if we have that M is a subset of N, right, a universe is a subset of the other universe, then we can characterize the substructure relation actually by using the quantifier-free diagram or simple diagram. So M is a substructure of N if and only if N, when interpreted as a structure over the extended language, where I introduce a constant symbol for every element in M, right, and then interpret those symbols as the corresponding element in M again. We denoted this by N subscript M, right? So M is a substructure of N if and only if this extended structure satisfies the simple diagram of M, where recall that the simple diagram, right? So this here is the simple diagram, collected all quantifier-free formulas and assignments to those quantifier-free formulas that are true in M. We now come to the first criterion for quantifier elimination. Suppose T is an L theory, phi is an L formula, then the following are equivalent. The first statement is just the quantifier elimination statement, namely there is a quantifier-free psi, such that T proves that phi and psi are equivalent. And the second statement is the criterion we want to apply to prove this. Namely, suppose M and N are models of T, and A is a common substructure to the two models. Then, for any A tuple in the universe of A, M satisfies phi of A if and only if N satisfies phi of A. The second condition may remind you a little bit of that of a being an elementary substructure. In fact, here we need to have this not only for M and N itself, but for any common substructure A. But of course, in particular, you can put A equals M, right? And then the requirement just says, right, from 2, right, if we have quantifier elimination, right, then this means that M is an elementary substructure of N. So in other words, if T has quantifier elimination, then for any two models of T, M substructure of N implies M being an elementary substructure. And any theory T with this property here, right, is called model complete. Model completeness is not the same as completeness, though. we will see, for example, that the theory of algebraically closed fields, ACF, fields has quantify elimination, but is not complete. Because you can have fields of algebraically closed fields of different characteristics. So we give the basic ideas for the proof of this criterion. One direction is not hard at all, namely from 1 to 2, that just uses the persistence of quantifier-free formulas between substructures. The direction from 2 to 1 is quite a bit harder. So here we have our formula phi, x1 up to xn, and now we just collect, we start by collecting the quantifier-free implications of t in t over t of phi in a set of formulas. So let gamma of phi be the set of all formulas chi x1 up to xn, so that chi is quantifier free, and t proves that for all x, phi of x implies chi of x. Now we extend the language by adding constant symbols for each xn, so c1 up to cn. So those are new constants. And now we can look at the set of formulas over this new language, where we just look at gamma of c, which would be the set of all chi of c, where chi is in gamma of phi. So we collected all of the quantifier-free consequences over t of phi in a set of formulas, and now replace the variables by constants. So what we would like to have is the following. We would like that gamma or t union gamma of c implies phi of c. Why is this nice? So let's call this condition star. If we had this condition here, t union gamma implies phi, right? Then by compactness, we could pick a finite subset of the of gamma. So let's say psi1 up to psi k, such that t union this and psi i's implies phi of c, right? And this here is quantifier free. So with a little bit of work, you can show that t proves that phi of x is equivalent to conjunction of the psi I of x. To show star, in turn, you assume that it's not true, so then the set of formulas t union gamma of c union not phi of c has a model. So let's call that M. and we look at A to be the substructure generated by the interpretation of the constant symbols in M. So C1 in M up to Cn in M. Now what you do is you take that substructure A and you take its simple diagram, right, and add it to T together with phi. So we have T union phi C and the simple diagram of that generated substructure A. And you show that this has a model and you argue this again by compactness. If this didn't have a model, then there would be a finite collection of formulas from the simple diagram of A that would imply not phi, and then you can turn this around and say that then phi proves a disjunction of those finitely many formulas, the negation of those finitely many formulas, and then you could show that there has to be something, would have to be something in the diagram, elementary diagram. In particular, it would have to be satisfied by A that it shouldn't satisfy. Okay, so this has a model. So N has, let's say N is a model of sigma. But now we are in the situation, we have M is a model and N is a model. Both are models of T and both contain A as a substructure. So M and N are models of T and both contain A as a substructure. Right? But if you look at the truth behavior, one was made to satisfy not phi, and the other one was made to satisfy phi. So we get a contradiction here to 2. So let me write this down. M would satisfy not phi of C, and N satisfies phi of C. And this would give us the contradiction with 2. Now we come to the second criterion. This criterion just tells us that it's enough to be able to eliminate existential quantifiers. So in particular, suppose for every quantifier free phi and for any variable x there exists a quantifier free psi such that T proves that exists x phi is equivalent to psi, then T has quantifier elimination. So this tells us that we can, if we can do it for existential quantifiers, we can do it for all formulas. And the proof of this is simply by induction on the height of phi. The height of a formula. Now we can combine the two criteria, and we get one final criterion that will be the one we'll be using in the next lecture. So here, let's call that a theorem. If T is an L theory, and suppose that for any two models, M and N of T, right, and for any common substructure A of M and N, right, and for any quantifier free phi x0, x1, xn, if there exists an tuple A in the substructure and a B0 in the smaller of the two models, right, such that we can make the existential statement or true in M, namely the existential exists x0 phi, right? So that means B0 is a witness to the existential statement exists x phi, right? Then there exists a C0 in the bigger structure, right? Such that in the bigger structure we have phi C0A. So in the bigger structure, C0 would be the corresponding witness to the existential statement exists x0 phi, right? So if this is true, right, then T admits quantifier elimination. So this is simply combining the two criterion. One says we can restrict ourselves to existential formulas, and the second one is this kind of substructure completeness, in the sense that if we can make formulas persist if we choose if we assign values from a common substructure. And here this is just written or spelled out in terms of this specific criterion only for existential quantifiers. Okay, and armed with this criterion, we will now in the next lecture look at quantifier elimination for a more complicated theory, more complicated than dense linear orders, namely algebraically closed fields.